So just to sort of start by recapping a bit from the last time. The key idea we've been having with these variational approaches is, so we've got this EIG, this expected information gain that's going to be the amount of information we're getting from an experiment. And what we're trying to do is set up an approach where we can kind of have this regressional estimate of some aspect in the expectation, and then we can optimize that regressional aspect by using a variational bound. So a lot of these bounds are guaranteeing, for example, this case that it's always larger than the actual EIG. So when we minimize it, we have a mechanism to sort of tighten that bound and train this variational approximation. And this gives us a way of both directly sort of doing the estimation for this bound. And we can also actually, in some ways, use them in making other bounds as well. So if we learn sometimes this posterior estimate, we could learn the posterior estimate with this bound and then use it in this slightly tighter estimator here. So we don't necessarily have to use sort of a really tight bound all the time to learn something, but then we can use one of these much tighter bounds like this one at the bottom to go and actually do the final estimation for our EIG. The problem we've got though is that even though we're maybe getting some quite good ways of approximating the EIG, we've only solved a quite small part of the problem. We're still needing to sort of do optimization of this. We still ultimately care about designs. This is only our objective that we're trying to estimate. We actually really care about optimizing it and getting those designs. And we're also sort of forgetting all of this sort of adaptive design at the moment. We've been doing all of this in the static setting, and there's going to be additional computation that's probably going to come in when we have to deal with that adaptive setting as well. So the next thing we're going to start looking to is how can we get around this issue about the fact that the optimization is very difficult. And historically, this has usually be done using some sort of two-stage procedure. So historically, we would say put something like Bayesian optimization or some other kind of black box optimizer as some sort of wrapper around this estimation, and then just use that as a mechanism of doing the overall things. We have this two-stage procedure. We'll have a wrapper-style global optimizer, and then when we need to estimate it, we can run this variational method. However, this sort of two-stage procedure is actually really quite problematic. It's generally going to be very inefficient. So each of these calls for each design is going to be very expensive, even though we're using one of these variational things. They're still not that cheap, and so we have to do it. And they're in particular inefficient because we're not sharing any computation between designs. So each time we have a new design here, we'd have to retrain a variational approximation again, pretty much from scratch. And we have this sort of inefficiency of lack of sharing. And that is particularly bad in that we'll often spend a lot of resources on unpromising designs. In practice, we only really care about having good estimates where the design is promising. We really don't care about having bad estimates if there's no chance that point is going to be optimal, where it's only our objective we're evaluating here. And we only really care about having good estimates of that objective in promising regions. Finally, most of these things are going to have to sort of treat the target as some kind of black box, and they're inevitably going to scale really poorly in the dimensionality of the design because of that. And so we've got lots of these reasons we want to avoid this kind of two-stage style procedure. And the solution is reasonably simple. The solution is just to sort of set things up in a way where we can simultaneously do our estimation and optimization. So we've just introduced a method for estimation that is itself basically based on optimization. It's estimation through optimization of that variational distribution. And what we want to do is just set up a system where we can simultaneously do that optimization and the optimization of the designs at the same time. And we can do that if we take any of these bounds we've just introduced, as long as they are a lower bound. So we want to maximize the expected information gain. And if we have a lower bound, then improving that lower bound is either going to give us a larger expected information gain or a tighter bound. So we have this unified objective by having a lower bound that we can optimize at the same time. And in particular, we're going to have, we want abilities to have sort of unbiased gradient estimates. So these bounds we've introduced, turns out we can generally just directly plug them in as a sort of stochastic gradient scheme. So if we just go back and have a quick look at one of them again, if we have, for example, if we have, say, this posterior one here, we can just draw samples from this outside, and we can calculate gradients of this term here. So we can just directly run stochastic gradient methods on this with respect to both theta and chi, so with respect to both, sorry, with respect to both phi and chi, so with respect to both our variational parameters and our designs. And so we just have this stochastic gradient schemes, and we can train them very much like we would train any other sort of variational method. In fact, they're going to look a lot like kind of a VAE in the sense that we're sort of simultaneously sort of training some kind of model aspect, which in this case is the design, while at the same time training something that gives us a tightness of this bound. And by contrast, we're doing this because we couldn't do this on the original. We saw that Nesta Monte Carlo is biased and it's not suitable for this sort of direct optimization. And essentially we're using these variational bounds as a sort of a replacement objective that we can work with and that we can go and optimize things simultaneously. And that's just going to take this very sort of standard form that we get everywhere else in variation inference, where each step we're just going to take some step size in some sort of gradient direction, where we're going to generate estimates of these gradients, which we can do by Monte Carlo. We can just draw samples from the outer expectation. So we can draw a mini batch just by direct sampling. Instead of a mini batch of data, it's a mini batch of the samples. And given the estimate, we'll get a gradient with respect to phi and a gradient with respect to chi, and therefore we can just sort of simultaneously step in these. So we're sort of looking at kind of a joint optimization surface in variational parameter space and in design space. If we climb up that space, we'll be able to learn our design. So we simultaneously do this. So as we get up, we're getting better and better approximations. So as our designs get better, as we get better designs, we're getting tighter approximations as we go. So when we start off, we might have very poor approximations, but that's okay. We just need a general direction to go. And as we start getting closer and closer to the peak, it becomes more and more important that we have these good variational parameters. So we have a good representation of the thing we're trying to optimize. And this tends to then work quite nice in practice. So to just give another quick visualization of how this is working, whenever we take a step, we're moving towards the peak of whatever bound we've got through our stepping in the variational parameters, and we're tightening the bound when we step in the variational parameters. So this combined effect is this sort of stepping up where we're simultaneously tightening the bound and moving at the slope, and looks very much like kind of EM or just sort of classic variational approaches. And the sort of bottom line with this is it just turns out to work very well. So we can actually run this, particularly in relatively high dimensional problems, quite a lot of the time. So variational methods often scale quite well. And so we can work in cases where, say, we've certainly tried it up to sort of hundreds of dimensions in our design space where there's no chance we're going to sort of run a successful Bayesian optimization or something to do an outer loop. But we can do this simultaneous training. And we can start to work with problems and actually successfully sort of solve problems that would be very much beyond the scope of the methods we had even sort of 4 or 5 years ago based on these sort of Monte Carlo approximations. So this results here are just from some relatively simple kind of regression problem that had 400 dimensions. And these top 3 methods are all variational methods that make use of slightly different bounds. So this ACE bound is a kind of contrastive loss. The PAC is another contrastive loss. And this Barber-Agakov bound is one of the ones we've directly looked at. And we have 2 values. We have the lower bound and the upper bound, because remember, we can't actually estimate the EIG unbiasedly. We can only get bounds on it. But we know that the true value is between these 2. We can very accurately estimate the bounds themselves. There's very little error in the estimation of the bounds. And so you know that the true value will basically be between these 2 points. And if you look at the bottom, the 2 at the bottom are sort of, this one's using Bayesian optimization with just variational estimation each time. So not doing this as a 2-stage procedure, not simultaneously optimizing designs. And this does generally very poorly. And we see there's a big difference between these 2. Also appreciate here with these differences that information lives on a log scale. So this is not sort of, oh, we've gained kind of twice as much type thing. It's a huge increase to it because it's sort of working in log probabilities. So you should think about these as kind of having log style units, entropies, of course, in sort of nats or in bits. And so this is actually in the context of experimental design. These kind of gains are really, really huge. These are very significant amounts of information we're gaining by doing it in these different ways. One complication we haven't looked at though is that we've so far assumed we can actually evaluate the density of the likelihood. We had these evaluations of P of Y given theta and chi, and actually that's often quite a unreasonable assumption. So it's in sort of a lot of the sciences, it's very common when we're doing an experiment, we have some sort of simulator for that experiment that can take in inputs and sort of predict, often stochastically, the outputs. But it's very rare that simulator is actually sort of a closed form density. It's usually something that will have some internal random variables, push things forwards and have some sort of random output. So we'll usually have some kind of thing that will have some sort of deterministic function. We'll have some noise, even if that's just, say, the random seed of your code. And then it will take in parameters and designs and give you outcomes. And this isn't enough to go and train and learn, just sort of train designs and learn these variational bounds with the things we've mostly shown so far. And what we need is some sort of lower bound that uses only samples and that we can kind of simultaneously work with both things at the same time. So the way this is usually done is by introducing what are known as a critic network or an auxiliary critic network. And that is essentially another thing that we learn as we're going. So it's something that will take the place essentially of the likelihood, and we can use it to learn that instead, and therefore sort of avoid ever actually having to evaluate the density of the likelihood. So probably the most popular and common approach when we're using critic networks is to approximate the log ratio. So we've got the log ratio of the likelihood over the marginal likelihood. So remember that the expectation of this guy is the EIG. So we're approximating the term essentially in the integrand. And this is essentially like running a classifier. This is the same basis on which sort of say GANs work, where they're kind of classifying if it came from the sample that had access to theta or the sample that didn't. And we can learn these things either just by sampling and sort of training them as kind of a classifier, or as we'll see in a sec, we can also do things with variational bounds. But the same idea is sort of as before, that we're kind of essentially learning this kind of functional approximation. And once we've learned the functional approximation, we can just go and use it with a sort of outer Monte Carlo sampler to go and do our overall generation. The problem though with just doing it in this way is it might be quite difficult to sort of do this as an overall optimization problem. So if we just say train a classifier, we're either going to have to sort of train a classifier for each of these chi, or we're going to have to sort of train some classifier that deals with all possible designs and then come back and do the optimization once we've trained it. What we want instead is more of a variational approach. And it turns out, again, you can use these kind of critic networks to form variational bounds. So one such bound is this so-called NWJ bound. That's actually quite old. It comes from much more sort of mutual information style things that are in quite different contexts to experimental design, but turn out to have a lot of the same terms. And it takes this sort of slightly strange form here. But it turns out this is just a lower bound, and it's only a function of things. So it's only a function in the expectations of this critic, and we have to draw samples. So we've got an expectation here over the joint. We can draw samples from that, and we can evaluate this critic that we're training. Then this is just a constant, it's a -1, and then we have an expectation this time over the product of the marginals, and then it's the expectation, sorry, the exponential of our critic function this time, instead of just the critic function. And it turns out that the slightly obscure looking thing is a lower bound that can in fact get tight as well with the right value of the critic function to the expected information gain. Another version is this info-NCE, which is typically used in contrastive learning applications. But again, it's a bound actually on the mutual information. And this one takes something that looks a lot more like the sort of NMC, the variational NMC bounds we had before. It has this contrastive thing where we include the 0th term, and we see here that sort of U phi in this case is sort of an approximation for the log likelihood. So it's kind of training a version of the log likelihood, and then by training this bound and training this critic alongside, we can go and do this estimations. It's worth pointing out with these that in general, you never want to use these sort of critic-based methods if you actually have access to the true likelihood. So here, this exponential of the critic is just equal. If the best thing this can be equal to is exactly the likelihood. So the best thing you can beat is the log likelihood, and we would just get another actual variational distribution free bound that is still a valid sort of thing we can work with for optimizing the designs. But the high level idea is these are replacements when we don't have the likelihood. They're not generally methods we want to use when we can actually evaluate the likelihood density, but they do allow us to just sort of work with simulators. And what's cool about these is that they really take it to quite sort of a minimal set of things we need to do this kind of Bayesian experimental design approach. We just need some prior over the parameters we're interested in, and some sort of simulator that can generate samples of outputs given that, and from there we can actually do everything else that we need. So I think this is a good time to again pause for questions. So does anything have anyone does anyone have anything they want to ask?
Are there any questions? We don't see any questions as of yet, so we can move.
Is the sound generally better than the first half, by the way, or worse? Because I can change it back if it's actually worse.
Is it better or worse? It's better. Thank you.
Great. Okay. So so what we've got now so far is we've got these sort of variational approaches where we can simultaneously sort of do our estimation and learning designs, and we can do this all as a sort of nice end-to-end stochastic gradient approach a la deep learning, and that's all very nice. But have we actually kind of solved what we needed to do? So let's go back and let's think about the problem that we had with these questions, and we can go and say, well, now we're going to ask, would you prefer £90 a day or £100 in a year? And the respondent says, I'd rather the £100 in a year. And then the sort of system goes, okay, well, now I need to go and do some optimization. And this is potentially quite a quick thing as these things go. You might be able to train this in a couple of minutes, but it's still hardly ideal. We're still sort of trying to do some relatively significant amount of computation in between each step of the experiment. And say you're trying to do sort of some advertising survey online, this is never going to be viable because people are not going to wait even sort of 2 or 3 minutes for the next question. We need basically the next question to come out almost immediately whenever we're working with human participants. And more generally, there's going to be a lot of more sort of say control style settings where we need very, very quick responses, and we need things to run in real time. And so even though we've done a lot of stuff to make this sort of more efficient and get a lot of the issues, this is still going to be expensive, and it still can actually be very expensive occasionally. So we can still looking at hours or even days if you have a very big, difficult model to do this computation, and it's just not viable to try and do that during the experiment itself. And the reason it's slow is that we've still essentially got to do sort of inference as we're going. So we've been focusing about how we optimize the EIG, but there's still this inference going on under the hood that we had to do between each iteration. And that's itself always going to be expensive. And we still have this optimization of the EIG. It's still kind of a separate optimization. It's not like a convex or very quick optimization. It's still potentially reasonably difficult optimization, potentially even involving neural nets that we're doing at each thing. And we want to get rid of this. We want to kind of strip this out and get back to something. And ultimately what we need is something that will adaptively work in real time. We want adaptive designs that we can actually run in real time and will actually therefore be useful for practical problems. And what people tend to do in practice is they don't go and do these basic experimental design approaches. Usually they go and do some sort of fast heuristic approximation where they basically have something that's not really doing any kind of machine learning or Bayesian statistics or anything, but is just some sort of hard-coded kind of hacked back-end process that will sort of try and be adaptive, but in a quite unprincipled way, but where it's really quick. It's sort of pre-coded, and it will very quickly make the decisions about what things to do. And so the question then, of course, is how can we enable this sort of adaptive experimentation in a way that is going to be fast, like heuristic, but actually still retains these nice aspects of Bayesian experimental design. We want these Bayesian optimal designs. We don't want to sacrifice how well we are designing because we need it to be quick. We want things to learn quickly. And the idea that we came up with this last year was that what we can actually do is, instead of thinking about the problem in terms of designs as the thing we want to optimize, we can actually think about learning a policy in the kind of way you would in reinforcement learning. So in other words, what we want to do is we want to learn something that takes in the history, takes in the previous things we've seen, and just automatically chooses the next design for us. We want to upfront learn this. We want to learn this as a function, and instead of learning the designs. And it's kind of very much similar to the sort of motivation we had from the estimation, where we said we're doing all of these estimations separately. Why are we learning? Why aren't we learning a functional thing here? And it's the same. Now we're learning a function that maps from data that we've seen to the next design to choose. And the motivation is slightly different. The motivation is we don't want any computation during the experiment itself. We want to do everything up front. But if we do this well and say learn this policy as a neural network, it can allow us to pretty much instantaneously do the design. So we're just learning some mapping function that takes history, predicts designs. And if we can do that, then we're sort of golden. We can go and run things very quickly, and we'll just have an experiment where each time we'll just evaluate this pi. We'll just feed it the data we've seen so far. So we'll evaluate pi with data ht-1. That will output the next design chi-t. We'll do an observation at chi-t that will give us a new data pair. That will update the history, so we'll get a new set of history. We'll pass the new history back into the this policy, and the policy will give this. So we can just immediately, continuously iterate this thing to run the experiment very quickly in real time. And in general, say this policy would often be, say, a neural network. We're going to be able to run this in milliseconds, or possibly even quicker, because it's just a sort of single forward pass we're dealing with. And the reason we can kind of do this is that remember that sort of the model sort of defined everything. We do every bit of computation we're doing is kind of building out from the model. And that sort of notion of optimality is just, it's this universal thing. If I have the model, everything is decided. And that kind of means that actually we can do all of this computation up front if we're very careful about it as an offline training. We don't need the information of the data we've gained so far to learn how we're going to act in the future. And so given this sort of prior and this likelihood model, we can do some sort of offline training to learn this policy. And we'll obviously come into how we're going to do that in a minute. But the key idea is that we can do this up front. We can do this as sort of an amortization, like amortized inference, when we learn this beforehand. And then once we've learned it, we just deploy it, and it just gets used again and very, very quickly. And of course, if we then want to do inference, we don't do the inference as we go. We don't have to actually keep track of any kind of posteriors during the experiment. The policy actually removes this need to sort of have posteriors as we go. And we just sort of, if we want to do inference, do it right at the end. We get the super fast process. And an interesting sort of hidden thing that's actually going to happen as well here is that it turns out that the sort of way we've been doing it before was actually sort of greedy. It was each time we were kind of assuming that the next experiment was our last. We were actually optimizing the expected information gain of the next experiment. Whereas what we really care about is the information we're going to get across the next set of experiments. If we've got, say, T experiments left, what we really care about is how much information we gain across all T of those. And it will be the case that certain choices for our next experiment will have better or worse sort of downstream ability to learn. And so we get this greedy non-myopic policy, greedy myopic policy from the traditional approach. It's actually suboptimal. So we could actually view that approach as a policy. It is its own policy. Its policy is to optimize the conditional information gain at each iteration. It's a very computationally intensive policy. And it's actually also a suboptimal one. It's suboptimal because of this greedy nature. And so if we sort of get rid of this, we could potentially also actually start doing better designs as well by having these look aheads and being able to do things in a non-myopic way. The question then, of course, though, is how can we learn such a policy? So we obviously need to be able to optimize this. We need a practical way of training things so that we can go and actually deploy them. And the starting point for this is just to sort of build on what we've already got. And that is that basically we generally want to maximize the overall information we gained in the experiment. So if we have 10 iterations, we had some information gain for each of those iterations. Information is additive, so we can just add up the information from each of those iterations. And we can say that the overall, the sort of total information gain is the expectation of the sum of the individual information gains. So this information gain is, as before, it's this conditional information based on the history so far, and the sum of these conditional information gains and then take the expectation, gives us total expected information gain. And as I said, this kind of comes about because they're additive. And so we can think about it in a different way. We can think about this also as the expected information gain from the whole experiment rollout. So this expectation of the sum and expected information gains is also equal to the expected information gain from the whole history HT. So this would be sort of the objective. If we just optimize this thing on the right for just the designs, this would be back to the static setting where we just upfront choose all of our designs because we're looking at the expected information gain from everything. But what's changed is that we're not optimizing for designs anymore. We're optimizing a function that will choose designs on the history. So we're having this nice thing of dealing with all the information at once. We're looking at this sort of joints. We're looking at everything being evaluated at the same time. But we're still being adaptive because the thing we are learning will be adaptive at runtime. It will actually adapt things, and we're learning a functional way of doing it. And we have this sort of total information. So we have this way that we're also breaking the myopicness of the sort of approach before. We're going all the way from end to end, and we're learning the policy. What's sort of more important is that this thing still sort of looks directly like a normal EIG. The fact that these things are additive gives us something where when we're actually doing this sort of look ahead, we don't have nasty issues particularly cropping up from the fact we're dealing with multiple steps at the same time. We can kind of work in this sort of forward look ahead way, and it's still generally going to look like a normal EIG. And that means we're actually going to end up being able to use very much the same set of variational bounds from before. We can actually go and use directly the same variational bounds, and we're just going to change how we optimize them. We're not going to optimize them in terms of designs. We're going to insert a function, and we're going to optimize the parameters of that function rather than the designs themselves. So just to sort of draw that home a bit more, this thing is a full end-to-end objective. So we're doing an expectation over rollouts. So we're sampling a value with the parameters, then we're sampling a full set of data from that. So HT is the full set of data from the whole rollout of this iterative experiment. And then from that simulation, we're taking an expectation and we're looking at the log ratio of the probability of that data given theta over the marginal probability of that data without. So we're working with this joints over everything, and we can just sort of evaluate these autoregressively. So if our policy is deterministic, then each time we evaluate this, the only thing we're sampling is the y's, the outcomes. Then we deterministically choose the next design from that, then we sample a new outcome. And so this thing becomes a random variable where each design is deterministic given its history, but each design in isolation is marginally random because its history itself was random. But we can evaluate everything. We just autoregressively evaluate these terms. So this guy ends up just basically being the product of the likelihood. So this overall likelihood is just the product t equals 1 to t, the likelihood yt given theta chi t, and similarly this p ht given the policy is just the same product but without theta, so it's the product of those modules. So both of these are things we can go and directly evaluate. So now we've got this generalization of the EIG. So we've essentially taken this EIG for a design and we've reformulated it in terms of a policy. We need a way of actually learning a policy, and the way I proposed to do this was by using a neural network. So we can simply set this thing up as a differentiable neural network, deep network, that takes in histories and outputs the next design parameters. And then it's just simply a case of optimizing the parameters of that network by maximizing the total expected information gain from our things. Of course, though, as we've seen from before, the total information gain is going to be intractable, just like the expected information gain. And so what we do instead is we go back and we use our variational tricks again. We optimize a tractable lower bound on this. And for this, we can pretty much use all of the bounds from before, but just sort of rewritten to be over all of the things that we're observing rather than just the last one. And in fact, we can actually be quite cute about how we do this. And there are some bounds that are sort of useful without even having a variational approximation in them. So the one we usually use in practice is this thing called the sequential prior contrastive estimation, or SPCE bound. And it's quite like the sort of some of the nested Monte Carlo bounds we had from before. It's one of the contrastive ones. We include the 0th term. But essentially what it does is it just uses the prior as the proposal. So if we go all the way back to before, then we had this sort of bound before, where we created this variational bound by kind of making an important sampling estimator of the marginal likelihood, and then optimizing the proposal of this. All we're doing here is basically using the prior as that proposal, so that these two terms cancel and we don't have any variational approximation. And we don't now stop needing to actually optimize the variational parameters. It's obviously going to be a biased estimator, but what we can do is we can use more samples. We can increase this M as a mechanism for getting this thing to be a better estimator and the bound tighter. And we just sort of directly do optimization in the space of designs without having to sort of worry about learning something variational on the side. So we're sort of there's obviously a sort of a bias variance trade-off here. And what we're doing here is we're taking something that's going to be a little bit more biased in general, but where we have a lot less to learn, and therefore it's generally going to be lower variance. But the key high-level idea of this is that this is just something we can run stochastic gradient descent on. It's something where we can draw samples from. So we draw one true set of parameters theta 0. We can draw a rollout. We can simulate data using a combination of our policy and that true set of parameters. And then we generate L of what are these called contrastive samples. So these are L samples also from the prior that we're going to contrast to. And given those samples, we just can evaluate this log ratio, where these, if we have a model where we know the likelihood density, these are just things we can evaluate. And then this is just an objective that we can directly train this policy on. So we've gone through a lot of quite complicated things to sort of get here, but this thing is actually a very simple thing to go and actually train. It's just a direct sort of pretty standard, almost kind of neural network style optimization, where we're just drawing our own data. We're sort of simulating our data. We've got a sort of kind of like a loss function given that simulated data, and we just do stochastic gradient descent to train this whole thing end to end. And we just take gradient steps in this in the parameters of our policy. We can also use different bounds. This is this SBC one I'm showing just because it's kind of the simplest one to use. But we can go back and we can use these bounds that we saw before for implicit things. So here, the critic network means we do have something else to learn. We're not just learning the policy. We have to learn the critic alongside the policy, but they will again allow us to work as they did before without requiring anything but samples. So here, if you look at these terms, the key thing is that they're expectations over something we can sample from. And then what's inside these expectations is just the thing we're learning, the critic in both cases. So in both cases, just the critic inside these expectations. And so all we need is a sampling process. We need a forward sampling process that samples parameters that we're trying to learn, and it samples data given those sets of parameters, and given that, these give us mechanisms to do it. And which one we use will depend on the context. So the sort of, for example, the NWJ tends to sort of be higher variance but lower bias. The InfoCE is higher bias but lower variance, and which one we want to use will depend on the context. But the key idea is that we have these relatively simple things to work with, and we can go and optimize them. So we can put these things all together into a bit more of an algorithm block, just to sort of try and tie everything together. So our starting point is to assume we've got some prior, and we've got some sort of likelihood function. That likelihood function may only be a sampler. We may not necessarily have the ability to evaluate its density, but we do have to be able to draw samples of outputs given these things. So this is a simulator for the true experiment. We'll simulate outcomes given instances of the parameters and designs, and we need a number of steps that we're going to have in our experiment. So how many steps when we actually go and do the experiment we're going to do. And we're going to basically do almost all the work before the actual experiment. We're moving all of that computation out of the experiment. We're doing it all up front, and then we're going to have a very quick way of doing things at test time. So what we're going to do is, just while we've got some computational budget, we're going to sample a true set of parameters, and we're going to set a history to the empty set. And then we're going to go through each iteration of the experiment. And at each iteration, we just use our policy to calculate the design at the next step. So we've got the chi-t is pi phi of ht minus 1. That's just using the policy to choose the next design. We then simulate the output. So here we're doing this before the experiment. So this is not drawing from the true distribution. It's not running the actual experiment. We're using our likelihood model and the fact that we've sampled a ground truth set of parameters to simulate the output that we'll get for that design and that true parameters. And then we're just updating our history to the sets of design outcomes we've seen so far, and we can just roll all the way through this. Then we just we assume we've done this in some sort of autodiff system, and then we just take a derivative all the way through the system, including the evaluation of whatever sort of variational bound we want to use. So we have some derivative variational bound. That bound will only depend on these things that we've sort of generated as we've gone through here, coupled potentially with our prior and our likelihood. And for example, we can just evaluate this SPACE bound. We've done this sampling. We can evaluate these terms here. Or if we don't have the densities, we can use this critic. And but the key is we can just differentiate through the whole forward sampling process. That gives us a way of taking derivatives, and therefore we can make an update on the policies. So each sort of iteration of stochastic gradient descent, we're updating this policy, so it's doing a better decision of the next design, and so it's getting a better estimate, and we're just learning this thing over time. Once it's learned, we just deploy it. It's not it's fixed. We don't have to do any training, and it's just feeding forward through that neural network. We're just evaluating it. We've taken the history, we evaluate it, that gives the new design. Then we run the actual experiment that gives us a new observation. We update the history, and we plug it back into the network to go and evaluate things. And so we have this way of essentially in pretty much milliseconds going and running this. And so what this will now mean is if you come along and you've trained one of these sort of DAD networks on this problem we've been having throughout, and we get asked, would you prefer £90 a day or £100 a year? Say we respond £100 a year, it'll take, I think for this, when we did it, about 2 milliseconds to then decide the next question it should ask is, would you prefer £95 a day or £100 in a year? And we see that we get a bit more information. Whereas if another person comes along and says, this person now says they want £90 a day rather than £100 in a year, the policy will make a different decision based on the fact that you got this different response. And it will very quickly ask, would you for £80 today or £100 in a year? And so we see that we're getting a clear adaptation between these two people, but we're being able to do it very, very quickly. I think this is probably another good point to stop for questions, if anyone have anything.
Is there any question? There is one question.
Hi, thanks for the really interesting talk. Just wondering, in this DAD approach, how much does the effectiveness of the approach depend on the parameter prior? Because I would guess that in the case where the parameter prior was no good, you'd be kind of sampling a lot in spaces that weren't actually relevant to the kind of ground truth setup. So you'd be learning the policy in areas of the state space which were kind of not necessarily important.
Yes, it can depend. I think a general rule of thumb is it can still work very effectively if your prior is over dispersed. So if your prior is over dispersed, you've hopefully still sort of covered the right areas, and it might take you a bit longer to train, but you've at least got some idea that those parameters might be there. If you've got a prior that's kind of quite off, and you have a sort of a true set of parameters that's basically not covered at all really under your prior, it's likely to struggle because it's sort of almost working a bit like a regressor, where it's kind of not envisaged that it could be all the way out here and it doesn't know what to do. So there is definitely there is definitely quite significant, actually, a lot of the time, dependency on not having too bad model misspecification. But you can at least control that by sort of making sure you're always erring on the side of sort of being over dispersed rather than sort of overconfident. So it will depend a lot on exact applications, but it certainly is something that's important.
Yeah, okay, thanks.
Any other questions? Okay, there's.
Hi. In your algorithm, the result is predicted using the all historic data. Is that is possible that if there is a Markov chain property that we just need the last p of the data to predict that?
Yeah, so if you did have some sort of Markov dependency, you might be able to do that. But I think it would be very, very rare to have that, because it's not even like it's some sort of time series. It's kind of saying that the only data that's relevant to prediction is literally the last point you've seen. So that the Markov property here would be actually in the data itself, not in your model or anything. So like, so yes, in principle, but I think it would actually be quite an unusual scenario where the history is of no relevance. Even if your model itself isn't like accounting for it, your policy might actually well sort of pick up on the fact that there's information it could have gained from the past.
Also, another question. In your method, theta is a time invariant parameter. When you sample YT from the time invariant, the distribution with the time invariant parameter theta, if that is possible, that the theta is time varying.
So theta is kind of global. There's not. You could. I mean, if you were trying to do some time series, you might have a theta that was sort of broken down into some global variables, and then you had a theta 1, a theta 2, a theta 3 for each time step. So that there's nothing sort of stopping theta being compounded into bits that have time dependency. But so we're not making any assumptions about the model here. This is just there is a prior. That's pretty much your only assumption. But how you construct that's very, very model dependent, and you could very much introduce time dependency into it if you wanted.
Are there any other questions? Not that I know. I see. So maybe we can proceed.
Cool. Okay, so I'm just going to skip over that because we're running a little bit behind. But the key idea is that we can keep iterating these things, and it does do sensible things. As you give a series of responses, we have gone and done this, and it does work. We can go and we can quite effectively go and automate this process of asking questions in a way that's generally actually better than a human experimenter would manually do by themselves. And numerically, what we find, which is quite interesting, is this policy-based approach doesn't just do well, it actually does better than this traditional approach. So we have this sort of slightly unusual thing, that this kind of almost amortized style approach, where we just have to learn one policy and we can use that policy for lots of different participants, is actually outperforming this one where we do this heavy computation at each style. So here, this sort of middle row, these are sort of upper and lower bounds on the true EIG, true total, sorry, EIG, that you get from doing this sort of traditional heavy approach. And we're actually getting better amounts of information gained by doing this. And this is kind of something that I think certainly surprised us, because originally the desire was speed. It was the fact that this thing was taking longer to run than we could do, and we wanted to get it down to tiny amounts of time so that everything can run quickly. We've removed that computation from experiment time, and we get this sort of thing that's doing better. And the reason for this is this thing I've already touched on about things being myopic and non-myopic. And what it turns out is that we're actually able to learn better than we're able to learn design policies that are better than the sort of optimal myopic design. So this greedy thing of optimizing EIG for the next step each iteration, we can actually end-to-end learn better policies than that kind of optimal way of doing it in this traditional framework. And it's this ability to look ahead, and it's probably best to sort of look at an example of sort of really why that matters. So imagine we're doing a very, very simple problem where we're just sort of trying to most evenly space some points on a line. The myopic thing is saying that I'm going to optimize this in the context of the next thing being my last. So the first thing it's going to do is put something exactly in the middle. But at the next experiment iteration, it's then forced to sort of put something at 3/4 or 1/4 because they're the next best place and the next thing. And we see that by sort of failing to sort of look ahead, it chose a poor first point that didn't account for the fact that the sort of certain early choices were better for downstream decisions than other early choices. If we do a non-myopic policy here, we'd do a spacing a third at the first point, and then after realizing the spacing a third at the first point, we put a second one 2/3 along. And so this sort of a look forward ability does give us this ability to sort of do better designs. And it turns out that this is actually really quite important and to do. And this look ahead, it turns out to be super important. And you might notice that some of this policy is starting to sort of encroach on kind of reinforcement learning ideas. And it's very well known in reinforcement learning that this ability to kind of have look ahead and sort of not be greedy is super important. So once it's trained, we've also kind of done this on the location sort of finding experiment. And we see that it kind of behaves a bit like it's showing in the video, where it was searching around, it finds the region, and it's learned to do a lot of samples there. And then it actually goes off and it starts exploring again. And eventually it finds this other region. And the sort of point I think that's important to make here is that it's kind of, there's a natural sort of ability to balance exploration and exploitation. So you'll probably seen in sort of when you looked at Bayesian optimization before that you've always got this idea of exploring and exploiting. And when you actually work with this sort of expected information gain, is the thing that naturally already balances these things. It's already taking into account that need for exploration and exploitation. There isn't a need to explore on top of optimizing this EIG. If you're optimizing EIG, you're already balancing these two things. And we really see it with this example here, where it sort of spends some time really exploiting that region because it's found that, but then after some time it says, well, actually I need to go off and search again and go back and try and find this other location. And for this location finding thing, we get even sort of bigger changes in speed. So it went from literally taking many hours to sort of run with this traditional approach to, I think it was 5 milliseconds it takes to run. So that this is very much slowed down here. It's actually 5 milliseconds from start to end. And again, we get really massive gains with improvement with how these things are working. Where we've been sort of looking to go with these things a bit more recently is to sort of start really scaling them up to some much more serious problems. So I've been looking at mostly sort of these toy things so far, but we're really confident that we can actually potentially sort of start doing some very high scale difficult things on sort of images. So with this, we work, I have sort of a collaboration with people that work with police sketches, and they're trying to do reconstructions of criminal suspects. So they've had an eyewitness to a crime, and people are very bad at sort of describing faces. They can't sort of themselves describe a face in a way that's going to sort of be a useful match to the suspect. But if you sort of show them images of faces, they're reasonably good at sort of saying, well, it's this one is more like them, or this person is less like them. And so at the moment, the company has sort of software where they will show them kind of 9 images like this. The witness will sort of say, well, I think 6 is the closest to the suspect. And then it will have some sort of heuristic algorithm that generates a new set of 9 faces, and then it will choose which they think is the best of the 9. And this just sort of proceeds quickly as a sort of a heuristic process. But we started to look at, can we kind of do this in a more principled way, where the design space is now literally the image, and we're trying to optimize for the images that we're showing people and working out. And it's quite preliminary. We're doing this in quite a simplified setting, so these are a little misleadingly good results. They're not actually quite as good as this. They're just sort of because the problem's been quite simplified. But we can actually get this to kind of start to work in this high dimensional space. So here we have an example where the sort of the true image of someone looks like this person at the top, and at the bottom is the series of sort of map estimates. There's multiple iterations between each of these, but these are sort of a series of map estimates for what the person looks like. And so at the start, we have a pretty poor approximation for this face, but over time, we quite quickly can get very, very close to actually reconstructing that under some sort of simulated scenario. So this is not run with real people. This is sort of simulated data under the hood. But what it does show is that we can actually do these things in quite serious, quite high dimensional design spaces in a kind of difficult and meaningful way. And it's potentially really quite exciting that we can start to work and we can start to adapt experiments in these sort of really quite non-trivial ways in these horrible high dimensional and difficult problems. So for the last little bit of the talk, and I'll go through this quite quickly because I appreciate it's already 5 o'clock. I just want to quickly talk about the other part of the title, which is in active learning. So active learning is a common area, and Bayesian active learning is quite a lot of research, probably more than the sort of general Bayesian experimental design I've been talking about. But what I really want to get across is that actually Bayesian active learning is very much a special case of Bayesian experimental design, and really it's important that we use the fact that it's a special case and exploit some of the things that we're utilizing experimental design in active learning. So just to take a step back and say what I mean by this. So active learning is based on the fact that we often have scenarios where we have huge amounts of unlabeled data. So we can trawl the internet for images. We can have huge amounts of images that are just trawled from the internet. But very few of them will often have decent labels. And so labeling data is often much more difficult and expensive in supervised settings than getting the unlabeled data in the first place. Another good example I think of this is you get it a lot in sort of astronomy, where they've got huge amounts of images of the sky and things, but very little sort of annotation of what is what for the sort of large amounts of things that have been gathered. And in this kind of scenario, we want to sort of basically utilize a lot of this unlabeled data to be very careful about which points we label. So if we've got a very limited budget in how many labels we can acquire, we want to be very careful about how we use that budget and be very targeted in the things we acquire labels for. And this is a special case of adaptive experimental design where what we're choosing is specifically which point to acquire labels for. So we have a sort of unlabeled pool, and each time we're choosing which ones to label, and that gives us an adaptive experimental design problem. And when we do this as an approach to train the model, when ultimately what we're trying to do is train some sort of supervised predictive model from inputs to outputs, and we're trying to choose the data we feed to that model and that training, that gives us this approach called active learning. So active learning is kind of like experimental design, but it's adaptively learning a model. So we're choosing our data as we train our model to make it as informative as possible. So to explain that a bit more formally, what we do is we start with some pool of unlabeled data. So we've got this D pool, which is just a set of unlabeled things. So we might have a big stack of unlabeled images. The second thing we assume is that we've got some sort of predictive model, and that might have got pre-trained on some other data. It might just be completely empty and random at the start, but it's going to take in inputs and it's going to predict something. So either the outputs directly or some probability distribution over outputs given some inputs. Given this model, we can define some kind of acquisition function that tells us sort of how useful it is to acquire a particular label. So we're hoping that sort of some images are more useful than others. If we've got this big stack of images, say we're sort of got a big stack of images and we're trying to figure out how to classify between breeds of dogs, the images that actually have dogs in are going to be much more useful than the images that don't have dogs in. And we don't know up front which ones even have dogs in, but we need some way of saying, well, these are good data points, these are bad data points, and we can use the model we've already got to get this kind of notion of usefulness. And then what we do is we just iterate through a process that's very much the same as the one we've been going through in experimental design, where each time we choose a design, in this case an input, at a particular point. So one of these, it's literally an index, we're choosing an index I, and then for that we acquire the label. We go and use whatever we have to actually go and acquire that label, that expensive process. And then we update our model. We update the model with the new data, in the same way that we say update our posterior in the traditional BAD approach. And then we can just iterate through this thing. So we're just updating our model with acquired labels, using that to do a new acquisition function of which point to get a label for, and just iterating through each of these things. As I've said this is a special case of adaptive design, where each design is the index of the point in the pool. The outcomes are the labels that we're requiring, and the variables we learn are the model parameters. We're ultimately training a model, but we can view the parameters of those models as some explicit parameters that we're trying to learn about, because if we've learned those parameters, we've trained the model. However, where it varies a bit from the experimental design setting is that because often those parameters don't have some sort of meaningful semantics. So in the sort of image reconstruction case, we were trying to refine a real image. There was real clear semantic meaning to what we were learning about. Here, usually the model parameters are pretty generic and arbitrary, and what we really care about usually is performance and just learning a model that does predictions effectively. And so we have this sort of slightly different emphasis. But under the hood, the process is the same as this general experimental design process. Then within the context of active learning, we also have the notion of Bayesian active learning, which is a relatively large subset, I would say, of the active learning literature. It's quite a big research field in itself. And what we do there is we just assume that predictive model has at least some Bayesian flavor. It's actually often not really Bayesian, but it has some sort of pseudo-Bayesian flavor. And specifically what it is that we assume it's the expectation of some predictive model over some parameters. So we have the f(phi) of x is the expectation over some distribution on some parameters theta of some predictive model given theta. So common examples of this would be sort of Bayesian neural networks, where often Bayesian neural networks aren't really sort of Bayesian under the hood. They kind of just sort of relatively crude approximations, but that they sort of practical algorithms in their own right. Another example would be sort of deep ensembles, where it's not even remotely considered Bayesian, but the sort of ensemble index is something we average over. And in both of these cases, they kind of conform to this form that is some expectation of some predictive distribution. And what we can do in this context is we can actually put that in the Bayesian experimental design context by treating this p(phi) theta as a prior and this p(phi) y given x and theta as a likelihood, and they together therefore give you everything you need to define an expected information gain. These things can still be iterative. I'm kind of hiding in the notation of phi here information about the history. So instead of sort of explicitly putting a dependency in the history here, I'm sort of pushing it through this dependency on phi. But the high level idea is that we have these two things and we can use those to define things. And what we then do is we define what's called the bold objective, Bayesian active learning by disagreement. And that's taken as the reduction in predictive uncertainty. It's the entropy. So if we look at the bold score for data point I, it's the entropy of a marginal predictive distribution of that point I minus the expected conditional entropy of that distribution. So we've got the entropy of pyi given theta xi. We've got the entropy of that, and we take the expectation over possible parameters theta. And so what we're looking at is basically, if we knew theta, how much is that reducing our uncertainty in predictions in expectations? So the expectation over theta here is an expectation over true values. And then for each sort of sample there, we can get the difference, the information we've kind of gained by knowing theta. And what we can see is that this thing is exactly equal to the EIG. This is exactly a form of the EIG in Bayesian experimental design. So although it's usually often thought about in the community, at least in the active learning community, as some separate entity, it's very much not. It is essentially a rediscovering of the EIG. So there's this sort of famous Holsby paper in 2011, but it's arguably that paper was really just a straight up rediscovering of a lot of the stuff that had already happened in Bayesian experimental design. But we can use it as a very interesting case. And we can use this as a mechanism for training models. And it shows us how we can use these ideas of Bayesian experimental design as more of a mechanism for model training rather than necessarily being so Bayesian. And we do that because we don't necessarily sort of consistently update these distributions. So p(phi) of theta has some dependency on the history. It has some dependency on the previous data. But it doesn't need to be an explicit posterior given that previous data. We can actually just retrain, say, an ensemble of neural networks again from scratch to get a new distribution of this. And we might have some sort of simple likelihood model associated with it. But we don't have to be sort of fully Bayesian with this. We can be kind of pseudo-Bayesian. And when we do this sort of pseudo-Bayesian approach that we see in Bayesian active learning, we are actually still doing this Bayesian experimental design style thing under the hood. One thing that's important to appreciate with this is the reason this has been a much more sort of prominent sort of use than a more general Bayesian experimental design case is that usually it's done in classification. And when it's done in classification, the expectation over y just becomes a finite sum. So you actually end up with something that is not a nested Monte Carlo estimator anymore. It's not something that has this double intractability because we can just estimate it using this thing here, where what we've got is a finite sum of mappings of conventional Monte Carlo estimators. So if there's, say, 50 classes or something, this is a sum over 50 different 50 mappings of Monte Carlo estimators. And so it's just going to scale in cost as the number of samples here, m, rather than having something that explodes in cost. It still can be quite expensive in practice, but it's still sort of tractable. So it's one of the sort of special cases where essentially the kind of outer expectation over the utility function that we had when we did this very sort of general experiment design all the way at the start, that expectation is just a sum over finite values. And so we don't get a nested expectation and it all becomes nice and easy. I'm just going to skip over that last bit, so I think we're very much running out of time. But I just want to quickly recap before we stop off. So generally, this talk's been about Bayesian experimental design, and we explained how that's something that uses a generative model to formalize the notion of experimental optimality. Namely, we look at the expectation of the information that's gained about some variables of interest. So we had this notion of we have something we want to learn about, and BED is a mechanism for formalizing how good an experiment is if we want to learn about that particular thing. We've in particular looked at how we can have sort of adaptive Bayesian experimental design approaches, and that we can use this notion of information gain and updating our beliefs as we go to give ways of sort of guiding experiments, having adaptive experiments that learn on the fly and adapt to the problem as they're seen. And we've seen also how we can use a lot of these variational approaches to try and do the underlying estimation. We've seen a lot of the bottlenecks for doing these BAD approaches are very much computational, and that dealing with those computational issues is often the real key to using them in practice. But these variational approaches really have quite a spectacular gains in how useful and doable things are. We've also spoke about this sort of recent advancement in working in policy-based ways, and how we can say that we can actually use a lot of these frameworks to learn policies like you would in reinforcement learning that can then just be deployed at use time rather than trying to optimize for the designs as we go. We can learn a policy that will make the design decisions for us, and that these can actually not only make things very quick and usable in practice, but they can actually give gains as well. And I think key with a lot of the talk and all of this is that these policy-based things are, I believe, pretty game-changing and what can be done. So Bayesian experimental design has been quite an obscure field, I think, for a long time. And I think it's been an obscure field because this computation is so extreme and has to be done during the experiment. But over the last couple of years, there's been these really big advancements in how tractable and how doable these things are. I think are quite game-changing and make Bayesian experimental design something that really is. It should be something we all care about, and I think will become an increasingly important thing. We've also spoke about how this sort of special case of active learning is one of the things. I've also alluded to the fact that you can actually formulate Bayesian optimization as well as a special case, and so I think these ideas really percolate down into a lot of other areas of machine learning. Finally, it's important, I think, to end on a slightly cautionary note with all of this, which is that basically to point out that sort of being adaptive in the data you acquire is actually slightly dangerous. And in the sort of a pure Bayesian setting, the likelihood principle would tell us that basically it doesn't matter how we acquire data, it's all the same. But in practice, and certainly in any kind of frequentist sort of way of looking at things, we can change our conclusions and we can change how we behave depending on the data we acquire. And we are very much breaking kind of conventional IID assumptions that you would make when you're doing, say, empirical risk minimization whenever we sort of do these adaptations in our data. And so it's very important whenever you do any of these things to think about any potential sort of downstream sort of implications they have or effects they can have on other aspects. And with that, I'll say thank you very much for attending and for listening.